Alright, so my name is Christopher Koontz, and I'm going to give you all a little presentation on the auto cycle. So first off, just a little background. So originally, the main reason that people started changing over into combustion engines is to try and, find a safer alternative to the dangers of early steam engines, specifically their boilers. And so there was many attempts at creating, an efficient combustion engine, but eventually German engineer Nicholas August Otto in 1876 created the first Otto engine, which was considered the most efficient engine of that time. And so basically what it does is it combines the process of intake, which is where you intake your fuel, compression, you compress the fuel, compress the gas, or liquid, either one, or liquids are incompressible, but and then you have combustion. So specifically in the auto cycle, you're gonna have a spark that's gonna initiate your combustion, and then your expansion, which is gonna drive your solenoid engine, kind of where like the power of the work comes from, and then your exhaust. The exhaust used energy or used fuel, and then you restart the cycle back over. And so basically, on a very low, very basic level, it's turning chemical energy into thermal energy, which then you can turn into motion. And this is obviously most common in automobiles, and you can have a 2 or a 4-stroke engine. So a 2-stroke engine is basically just completing the cycle in 2 revolutions, and so then you can probably guess what a 4-stroke engine does. It completes this cycle in 4 revolutions. And so a little diagram of this would be, most likely this would be the diagram of a 4-stroke engine. But anyway, you have your crankshaft and your cylinder connected to a piston, or within a piston, or covering a piston, and you have your exhaust valve and your intake valve, and your crankshaft rotates the piston and intake, then your piston comes back up, compresses, you have a spark, combustion, goes back down, and then when it comes back up, it exhausts in it. And just kind of go into a deeper dive to the process of the auto cycle. So you have kind of like steps, and so from 1 to 2 is your isentropic compression, and so entropy stays constant. You have a slight increase in pressure and temperature, so you can see from 1 to 2, and you're decreasing the volume, increasing the pressure and temperature, and so then you move into your isochoric heat absorption. That's where you have a spark, your combustion occurs, and then you have an extreme spike in pressure and temperature. So from 2 to 3, you can see the spark, and then that moves you to an isochoric is constant volume, if you ever want to know. But then you move to your process from 3 to 4. So then you have another isentropic process, isentropic expansion. And so this is kind of where your work is being done by your system. So you have that combustion, drives the piston down. The system is doing work, and then like your first isentropic expansion first isentropic process, your volume increase. You have a volume change, but this time your volume is increasing, and it's adiabatic. And so you can see that from 3 to 4, your volume expansion, your volume increase, and when the piston drives down, is when the work is being done. Then you have your final process, which is your isochoric heat rejection, so your second isochoric process. And so as you can tell, it's 2 isentropic processes and 2 isochoric processes in the auto cycle. And so then kind of opposite from before, your pressure and temperature, they decrease, and then this is where your exhaust occurs. And so you can see on the final part, your piston's going back up, your exhaust goes out, and then you repeat the cycle. And so for an ideal auto cycle, this is what your PV and TS diagrams are going to be. So you can see from 1 to 2, your decrease in volume, your increase in pressure, while also having constant entropy and an increase in temperature. Then you can see from 2 to 3, your isochoric process, volume stays constant, high spike in pressure, high spike in temperature, entropy increases, and then, kind of the opposite of that for your final two process steps. And so getting into the equations of the Otto cycle, the basic equations. So you have from the process you had heat addition, heat rejection, network, and then you're gonna have efficiency, which you kind of base the success of your engine off of, or success of the cycle off of. So your heat addition is gonna be your volume specific heat with your mass flow rate multiplied by the temperatures of the steps that you're going through. So you're only gonna have heat addition from 2 to 3, and so then it's going to be kind of the opposite, or it's going to be similar but with different steps or different points. So you're gonna, for heat loss, you're gonna have your mass flow rate times your volume specific heat, and then multiplied by the differences in your temperatures of your steps, and then your network is simply just the difference between your heat addition and your heat loss. And then your efficiency is simply your network divided by your heat addition. And so the heat addition, rejection, and network are pretty self-explanatory, but then I want to go a little bit more into your efficiency equation, because this is, like I said, kind of where you determine the success of your engine. And so you have, once you kind of manipulate your original equation, you're going to come out with your thermal efficiency equals 1 minus your heat out divided by your heat in. And so, since from the previous equations that you saw, flow rate, mass flow rate, and your volume specific heats are going to be the same. So you can cancel those out, and now you have your difference in temperatures. And for an isentropic process, your temperature, your one temperature divided by the other temperature is going to equal, the volume divided by your second volume, but reversed from your temperatures. So T2 over T1 is going to equal V1 over V2, and then you're going to have, it's going to be to the power of your specific heat ratio minus 1. And so and then for your isochoric process, your volume is going to equal, through those steps, so V1 is going to equal V4, V3 is going to equal V2, and then you can manipulate your equation that you just had to say that T2 equals T1, or T2 divided by T1 equals T3 divided by T4. And so then now you go back to your efficiency equation, you manipulate your terms, and it eventually gets you to an equation that is 1 minus 1 over your volume ratio to the specific heat ratio minus 1. And then so in combustion, you're gonna have a compression ratio, which is just your volume ratio, which is V1 over V2. And so this allows you to come down to simplify everything down to your thermal efficiency is going to be 1 minus 1 over your compression ratio to the power of your specific heat ratio minus 1. And that's going to be kind of what you use to determine how your how your engine auto cycle perform. That's my sources. That's it.
So the question I have, does anybody have a question there? Okay, like just go to the slide where you show us the equation for the thermal efficiency. Yeah, this.
Yeah.
So looking at this equation is very interesting. It's telling me that I can make my efficiency 100%. Are you guys seeing this? How do I make it 100%? I will just make R very large. It's meaning make R very large, right? Because if R is very, very large, what will happen? That side will get close to 0, right? And then you have like, But my question to you is that, is there a limit to R in an auto cycle? Yeah, to
Well,
this compression ratio.
Well, your efficiency is never going to be 100%. So you're never going to be able to get, you'll never be able to get, kind of what you're saying.
Yeah.
So there will be a limit to R, depending on kind of the size of your piston or whatever you're using. Because your ratio is just going to be, it should never be enough to cause your efficiency to be 100%. So it's going to be based off of or it should be based off of the size of your engine.
If I get what you're saying, the R is just based on the size.
Yeah, it's your volume. Your R is just your volume ratio of your points.
I see, but like, do any of you have why the R is very, very critical in an auto cycle? You can't just play with it anyhow. The fact that we can make R very big, but we can't because of one problem, who knows? Have you guys not heard of knocking, like when your engine knocks? What happens when the compression ratio is high? What will happen to the temperature?
It increases.
It becomes very hot. And remember, this is an auto cycle, right? The fuel and the air are inside the engine. So imagine your engine not sparking when it gets to the top dead center. Like probably halfway, the combustion has happened. So that will cause knocking. So because of that, how in an auto cycle, it's always restricted. Why? Because of knocking, effect of knocking. But for a diesel engine, it's different. Why? Because you're injecting the spray. In fact, we even want the head to be very, very hot. So if you look at a diesel engine, and just check it out, your diesel engine are actually longer than your auto. For those of you that actually look at this stuff, diesel engine is kind of longer than the auto. It's just because of knocking. That's why you can't really increase the compression ratio.